All right, today we're going to go on with lesson 21.3, angle-angle similarity. What we're trying to figure out is what makes two angles similar? What are the features necessary for them to be considered similar? So using angle-angle similarity postulate. The angle-angle similarity postulate states that if two angles of one triangle are congruent to two angles of another triangle, then we can call those triangles similar. So, in this case, for example 1, explain whether the triangles are similar. We're looking for two angles that are congruent in both triangles. In this case, I already have angle B of 100 and angle E of 100 being congruent. What I need is one more angle, and currently 35 and 45 are not congruent. But what I can do is figure out the missing angles here, C, and in this case D, to see if C is congruent to F or if D is maybe congruent to A. If I do have two angles congruent in both triangles, then we can call them similar. So let's see where it goes. I know that all three angles added together need to equal 180 degrees for a triangle. So 100 plus 45 is already 145. In order to figure out what the missing angle C is, I need to take away 145 from 180. And I'll be left with 35 for angle C. Now that is the same as angle F here, 35. And if this is 35 and 100, then 45 is going to be my missing angle D. And because the two angles in one triangle are congruent to two angles in this other triangle, we can call these triangles S for similar. Let's figure out whether these triangles in number 3 are similar. If I look at these two triangles, NOP and RSQ, I can see that they do share a similarity in the angles that equal 70 degrees. Now I need to figure out what the other two missing angles are to know whether we can call these triangles similar. If this angle is 49, 70 plus 49, I would add to figure out what the two come together is. So 9 plus 0 is 9, 7 plus 4 is 11. I have 119. Now I'm going to take 119 away from 180 in order to figure out this missing angle Q. I will borrow 10 minus 9 is 1, 7 minus 1 is 6, and 1 minus 1 is 0. So this angle has to be 61 degrees. Right now, what I can tell is that I still only have angle 70, angle R, and angle P congruent, and there is no 49 degrees or 61 degrees in this triangle. However, I still haven't found N. So let's see if I can find the value of N to determine whether they are similar. If 70 plus 58 gets me the total of the two angles that I do know together, that is going to be 128. Now I can take away 128 from 180 in order to figure out the missing angle. So I will borrow 10 minus 8 is 2, 7 minus 2 is 5. The missing angle here, N, is 52 degrees. 52 degrees also doesn't match either of the angles left over in this triangle. So explain whether the triangles are similar. In this case, we would say no, they are not similar because they only have one set of congruent angles in the triangles, not two. Again, you need to have two angles congruent to each other from both triangles in order to be considered similar, and in this case, we do not have that. Let's use what we do know in order to be able to put this into practice, finding missing measures in similar triangles. Because corresponding angles are congruent and corresponding sides are proportional in similar triangles, You can use similar triangles to solve real-world problems. For example, here. Example 2 says, while playing tennis, Matt is 12 meters from the net, labeled here. And this net is 0.9 meters high. He needs to hit the ball so that it just clears the net, meaning it goes past it, and lands 6 meters beyond the base of the net. So it needs to go from here, past the net, 6 meters further. At what height should he hit the tennis ball? We need to figure out what we do know. We do know that from the base of the net to where he wants the ball to hit is 6 meters. And we do know that from where he is standing to the net is 12 meters. These two line segments are going to be what we use to compare. And what we're trying to figure out is his height, and what we want to compare to is the height of the net. So in similar triangles, corresponding side lengths are proportional. We can set this side length of AD, the entire figure, over AB, and set it equal to the heights, DE over BC. So we're always going to put the larger length above and the larger height above, and then the smaller ones below, okay, in the denominators. So let's find what the length of AD is. AD is 12 plus 6, right? We have to add these two together, over AB, which is 6. And we set that equal to the proportion of the heights, DE, labeled as H because we don't know it, and the net, which is 0.9. So we'll do some math. We will go ahead and add what we know. 6 plus 12 is 18 over 6 equals height times 0.9. Now, since we're dividing, we're going to use a little bit of algebra and inverse operations to figure out how to get H by itself. Since we're dividing, we're going to multiply by 0.9 instead, so that these two can cancel, and we multiply by 0.9 on this side. So here we'll just be left with H once they cancel, and what we'll do is simplify this fraction. 18 divided by 6 is 3. So 0.9 times 3 is 2.7. That means his height, where he needs to hit the ball from, is going to be 2.7 meters in height. So what we want to do is set all of these values proportional. The length of the entire triangle proportional to the length of the smaller triangle. And the length, or the height, of what we're trying to figure out proportional to the height of what we know.